All right, hello, grade 8. So we're gonna discuss about the exercise 2. So it's actually the mid test from last year. And we gonna discuss it starting from question number 1. Okay, number 1 is quite easy. So you are given the pictures of the vibration in a pendulum, right? So here there is a movement from P, Q, and R, and then you need to find the movement of one vibration. So if we start from P, so it's supposed to be P, Q, R, and then Q, and then back to P. So it's actually the movement of one vibration. So it's actually until it's back to its position, but pass through the equilibrium position. And here the equilibrium position is Q. So the answer is, okay, we start from P, Q, R, P, Q. Okay, it's wrong. It's not following this pattern. And we start from Q, so it's from Q, and then go to P, go to Q, go to R, and then go to R. It's supposed to be go to Q again. And then if C, it start from R, so R, Q, P, Q, R. Okay, this one correct. C, right? And then for D, what's wrong with D? Q, P, R. It's supposed to be go to Q first and then go to R and then back to Q. So the answer for question number 1 is C. Okay. Okay, the next one, question number 2 and also number 4. Right, so question number 20. So there is a spring that is hung in a stative and then on the release, the load moves up and down 20 times in 25 seconds. And then you need to find out what is the spring period, right? So we know that the number of vibration here is 20 times, whereas the time here is 25 seconds, right? And then the question, you need to get what is the period, right? So to count the period, we're going to use period equals to time over n. So it means 25 divided by 20. So you're going to get 1.25 seconds. So the answer is C. And then question number 3, the pendulum moved from A, B, C, B. So from A, B, C, and B, it's take 3 seconds. So here the time is 3 seconds. And then we need to find out what is the frequency. So the question is asking, what is the frequency? Okay, how we count the frequency? We must to know first what is the number of vibration that we have if it's moved from A, B, C to B. All right, so we need to know what is the one vibration. The one vibration, we start from A, so it's supposed to be A, B, C, B, A. So you can see here, so there are 1, 2, 3, 4. There is a 4 section, but for the given information, it's only 1, 2, 3, only 3 section. So from here, we can count that the number of vibration when it's moved from A, B, C, B is only 3 over 4. Okay, and now we can answer to count the frequency. Frequency is counted as the number of vibration in a certain unit time, right? Or per second. So it's mean n divided by t. So n is 3 over 4 divided by the time is 3 seconds. So it's same with f equals to 3 over 4 times 1 over 3. Or we can just 3 times 1 over 4 times 3, it's mean 1 over 4 hertz. So the answer is A. That's question number 3. Okay, the next one, question number 4. Okay. In question number 4, you are given the spring here, right? Okay, the spring, the load moves from A, O, B, O, A. Okay, so let us see here. It's moved from A, O, B, O, A, O, B. Oh, it's quite a lot. Okay, and it's happened in 0.3 seconds. So the time is 0.3 seconds. So we need to know how many vibration is it, right? So we start to check if one vibration, so it's moved from A, and then O, and then B, and then O, and then back to A. So this is already one vibration. So from here, here, and then back here and here. This is one vibration. So if we know there are 1, 2, 3, 4, 4 diffusion, right? But the questions that given here, the movement that's given in the question is from A to O1, O to B2, B2 O3, O to A4, A2 O5, and then O to B is 6, right? So if we compare here, the number of vibration here is actually 6 over 4 vibration. Or in other words, it's actually same with 1.5 vibration. Okay, and now the question asking what is the frequency again, right? So to answer it, frequency is equals to the number of vibration over time. The number of vibration is 1.5 divided 0.3. The time is 0.3 seconds. Make it easier for our calculation, we can times everything with 10. So we're going to get 15 over 3. This equals to 5 hertz. So the answer is delta 5 hertz. Okay. So the next one. Okay, question number 5. For question number 5, you are given several quantities here. And then you need to find out what is the factors that influence the period of pendulum swing. Remember that in the pendulum swing, the period is actually can be counted as 2 pi square root of L over G. So L is actually the length of the rope. And then G is actually gravity, right? So mass will not affect the period of the pendulum swing. The density, no. The gravitational area, yes. The gravitational acceleration, yes. The rope, yes. The amplitude is not. So only 3 and 4. The answer is D. Okay, the next one. Question number 6. Rio is using a tuning fork that has a frequency 440 hertz. So the given information, the frequency is 440 hertz. And it is vibrate for 5 seconds. So the time is 5 seconds. The question, what is the number of vibration of the tuning fork? All right, so the question asking about what is the number of vibrations? So it's mean N, right? So to answer it, we need to remember that frequency is counted as number of vibration over time, right? The number of vibration is the question. The frequency is given. The frequency is 440. And then the number of vibrations is the question. The time is 5 seconds. So to get N, we know that it's supposed to be 440 times 5. We move 5 here, so it's become multiplication. So N equals to 440 times 5. So it's going to be 0, 20, so 22, so 2,200 vibration. Or some people just call it, yeah, the times of vibration. So it's D, 2,200 vibration. Okay, that's question number 6. The next one. Okay, number 7. Okay, we start with number 7 first. Okay, for question number 7, given that the mass that is suspended by a spring with a constant spring 1,000 Newton per meter, right? So it's given information, the mass is 6.4 kilogram, and then the spring constant is 1,000 Newton per meter. And then it's pulled and released so that the vibration is occurs, right? And then you need to find out what is the period of the spring. Okay, so to solve this problem, I hope you still remember that period in spring, we count it as 2 pi square root of m over k. And 2 pi is just the, what do you call it? The constant. So we just put it as a constant. The mass here is 6.4 kilogram, and then the k is 1000. Okay, the mass must be in kilogram because the spring constant is in Newton. So Newton must be equivalent with kilogram. So whenever you have a question with Newton, so it means the mass must be in kilogram. Okay, so now we count it. So 2 pi. Okay, so it's a little bit hard for us to get what is the square root of 6.4. So we can change this number, become 64 over 10,000. So we can do it because like when the upper part is times 10, so the lower part also must be times 10. Okay. So t equals to 2 pi, and then for this square root, 64 over 10,000 can be changed into square root of 64 over square root of 10,000. So square root of 64 is 8, and then square root of 10,000 is 100. So you have 16 pi over 100, or t equals to 0.16 pi. So the answer is C. And that's question number 7. Okay, the next one. Okay, the next one, question number 8 and 9. You are given several events here, all right? From the events that above that produce longitudinal wave, the pool water which initially comes, suddenly a small branch fell into the pool water. So actually it will make a ripple in the water, and that ripple is actually the transverse one. So it will create the transverse wave. And then when the rope is tied to a pole and then the other end is moved up and down, it's also gonna make the transverse wave. As you remember that the direction of this rope is actually horizontal, and then the direction of the vibration that you're gonna give when it's moved up and down is actually the vertical one, right? And when the direction of the propagation and direction of the vibration are perpendicular, so you're gonna get the transverse wave. All right, then the next one, the slinky that is moved back and forth. So if you move slinky back and forth, so some part of the slinky will make the compression, which is a very neat and also very close to each other. And then some part of the slinky will make the rarefaction that's quite rare from one to another. And this is actually the longitudinal wave. Okay, so this is including as the correct answer. And then Andre's singing was heard by many people. When it's talking, it's about talking or it's about singing. So it will produce a sound. And sound also a longitudinal wave. Longitudinal wave. So the longitudinal wave is 3 and 4. The next one, number 9. An astronaut who conducted the research on the moon can communicate with a visitor on Earth using radio waves. As you know, that radio waves means that it used the radio waves. And radio wave is actually one of the examples of electromagnetic wave. And as you know, electromagnetic wave doesn't need any medium to transfer. Okay, so the event showed that the type of radio wave is electromagnetic because it can propagate without a medium. Okay, right. So that's for number 8 and 9. So now we're gonna discuss question number 10 and also 11. Number 10 first. You are given some of the activities and then the activities that show transverse wave. Matthew singing when Rika hears him. So this is the longitudinal one because it's about sound, all right? Michelle is looking at the ocean waves coming to the beach. So this is actually the transverse wave because the wave will make this kind of a wave, right? The ocean wave is like this, so this is transverse. So this is the answer. Then Jennifer is chatting with friend. Again, chatting here means talking with her friend. So talking is about the sound, so it is longitudinal. And then Robert playing slinky and move up and down. So this is the opposite with before. So the slinky is move up and down, so it will produce this pattern as well. So this is also the transverse one. So the transverse wave is actually 2 and 4. So the answer is Bravo. That's question number 10. Okay, next question number 11. Okay, you need to find out. You are given the C wave, right, as shown in the pictures on the graph, and you need to find out what is the maximum amplitude of the C wave. So remember, whenever you have to count what is the amplitude, you must know, or you must get what is the undisturbed position, or we also can call it as like the equilibrium one, or the main axis of the wave. And here on this question is at this line, thread 1. Okay, so next, the amplitude, you just need to measure it. What is the distance from the highest peak to the, what is the distance from the highest peak to the main axis or to the undisturbed position? In this question, the maximum is mean the highest one. The highest one, I think this part, right? So it's actually 1, 2, 3, 4. So it's supposed to be 4 meter, so that the displacement is in meter. That's question number 11. Okay, the next one. Okay, number 12. You need to get what is one wavelength shown by the pictures there. So it's about transverse wave. Remember, in transverse wave, one wavelength, so it means one crest plus one through. Or you also can call it one hill and then one valley, right? So for number 1, it's from here to here, all right? So it's more than one crest and one through, right? Number 2, it's more than as well. Number 3, just half of the crest and then just one through. So it's not even one, right? But number 4, we can check here. We have half of the through plus half of the through. So we have one through, yeah, half. So it's mean one through. And then this is another one crest. So in total, you're gonna have one through and then one crest. So the answer is 4. Okay, that's number 12. Then the next one, number 13. On number 13, you are given the longitudinal wave, right? And you need to find out what is the wavelength. So it's say that there is a distance 20 centimeters. So from this question, we know that S is equal to 20 centimeter. And then we need to find out what is the wavelength. We need to know what is the number of waves that we have on this 20 centimeter. The number of the wavelength that we have here, as you know that one refraction, one compression, one refraction, this is already 1. And then one compression again, another one refraction, and then one compression, another one refraction, and so does this one. So in total, we have 1, 2, 3, 4. So the number of waves that we have is actually 4 waves. And the question asking what is the wavelength or lambda? We can count that wavelength can be counted as the distance over n, or the distance divided by the number of waves. So here 20 divided by 4. So number of waves, the wavelength is 5 centimeter because the 20 is in centimeter. So the answer is A, 5 centimeter. That's question number 13. Okay, the next one, question number 14. You are given the transverse wave, right? And then you need to find out what is the wavelength of the wave above. So as you know here, so we can draw this. So it has 1.5, right? So it's actually consists of 1.5 hill and then 1.5 valley, right? So 1.5 valley. So if we're talking about something like this, so it means it's actually 1.5 waves. So this is the number of waves. So n is equals to 1.5. And we know that at this distance, the distance that we have is 18 centimeter. And the question asking, what is the wavelength, right? What is the wavelength? So again, to count the wavelength, we can count it as lambda equals to S over N. S here is 18 centimeter divided by 1.5 waves. So in one wave, or lambda is 1.18 divided by 1.5 is 12 centimeter. So the answer is C, 12 centimeter. That question number 14. Okay, then the next one, number 15. There is a slinky, and the slinky is moved back and forth regularly so that 4 compression and 4 refraction are formed. So from this information, we know that the number of wave is 4 because for the longitudinal wave, it's made of 1 compression and 1 refraction for one wave. And in this question, we have 4 compression and 4 refraction. So the number of wave is 4. Then if the length of the slinky is 180, so the S is 180 centimeter, then the frequency is also given. The frequency is say that 80 hertz. And what is the question? The question asking what is the speed of the wave, right? So question is asking what is the speed. And you know, to answer this, to count the speed or the speed, we need the information about lambda and frequency, because sometimes we count it as lambda times the frequency. We also can use the other formula like V equals to lambda over T or V equals to distance over time. But in this case, we don't have the information about the time for this much distance, so we should not use this formula. And for this one, we need to count what is the period. It's okay if you're willing to count the period using the frequency information we have here. But for me, I prefer to just use the lambda times f, right? So the first things that we need to do is actually find out what is the lambda, right? So we can count lambda by using the information here. So we know that lambda is actually S over N. So we count it as 180 over 4. So we got the lambda is 45 centimeter. Because all the option in meter, so you must change this 45 centimeter into meter. So we're going to have 0.45 meter. And now we're back to calculate what is the speed. So lambda is 0.45 meter times the frequency is 80 hertz. So we're going to get 0.45 times 80. So the answer is 36 meter per second. So the answer is C. Okay. Right. So if you notice, hertz is actually same with the per second. So that's why even though it was hertz and then it's just changed into hour second. Okay, then question number 16. There are some of the statement given there, and then you need to find out from the statement above the correct properties of wave. Okay, what is the properties of wave? Wave can propagate, yes, all right. Wave can move energy, I think so, right? Wave can be reflected, yes. Wave can move the matter, no. Wave can be refracted, yes. Wave propagate always use medium, not really, because we have the electromagnetic wave. It doesn't need any medium, right? Doesn't need medium to propagate. So the answer here is 1, 2, and 5. Oh, wait. 1, 2, 3, 5. 1, 2, 3, 5. Okay, so the answer is A. So that question number 16. Next one, question number 17. Okay, there are the picture of astronaut there. All right, the astronaut does not communicate directly with another astronaut as we do on Earth, but rather through a communication device such as a telephone, because the temperature is extremely low. No. The moon's gravity, not really. It will not affect the sound. On the moon, there is no air as the medium of sound. Yes, because there's no medium of sound. It's a vacuum, so we need a device to communicate. Doesn't produce all light. Yes, it's true, but it doesn't have relation with the sound. So the answer is C, because it doesn't have a medium for sound to travel. That question number 17. Okay, the next one, question number 18. Okay, a child plugs a guitar string and then causes it to vibrate 30 times in 0.5 seconds. So from here, quite clear that N is 30 and then time is 0.5 seconds. Okay, and the question is, you need to categorize what is the type of the sound that is produced. Okay, so to categorize that sound, we need to know what is the frequency, right? So we need to count the frequency first. F is equals to 30 over 0.5. If you still not remember the formula, that frequency is counted as N over T because it's talking about the number of vibration in a second or in every second. So 30 divided by 0.5, so it's 300 over 5. It's equals to 60 hertz. And you know that 60 hertz actually already in the limit of the audiosonic, whereas the audiosonic is actually from 20 hertz to 20,000 hertz, right? Okay, so here is including as the audiosonic. And of course, it means that people also can hear that. Okay, that's for the number 18. Then the next one, question number 19. Question number 19 is talking about some properties of sound, right? And this there are some statements there, and you need to find out which one is the correct one. So first, the tone or pitch is determined by the amplitude. No, it's determined by the frequency. Okay, and then the next one, the tone or pitch is determined by frequency. Okay, it's correct. The loudness is determined by frequency. No, it's by the amplitude, right? So this one is not also. The loudness determined by amplitude is correct. So the answer is 2 and 5. So it's Bravo or B. Okay. Okay, the next one, question number 20. Okay, the next one. Okay, the next one, question number 20. All right, you are given 4 waves here, and then you need to find out the correct order of pitch or frequency from the highest to the lowest one. The highest frequency, it means that more waves in a second or in a certain unit of time. So if you can see here, the one that has more wave is actually wave P, or this is the most that has most wave in a certain time that is given here. So the one with the highest frequency is supposed to be 1. And after that, the second one is wave Q or 2, because it has a 2.5 wave. And then the next one is 3, because 3 has 1.5 wave. And then the last one is wave S, because it has 1 wave. So the answer is 1, 2, 3, 4. So it's already in order. So that's question number 20. Okay, the next one, question number 21. Okay, you are given a tone here. I think we will do it together. Okay, question number 21 and 22. So you are given the frequency ratio of the tone, and then it says that the frequency of tone E is 330 hertz. And then you need to find out what is the frequency of tone F, all right? So in order to count it, we just need to use the frequency ratio of F over the frequency ratio of E, gonna be equals to F is here, so this is 32, over the E ratio is 30, right? So please make sure that the ratio that you put here is belong to tone F, and then the ratio that you put here is belong to tone E, right? And then the frequency of F is the question. The frequency of tone E is given 330 hertz equals to 32 over 30. If you want to simplify these numbers, okay? You can just simplify this. So it's going to be 16 over 15, right? But if you don't want also, okay, right? Because I think the number is going to be easier if we have 32 over 30, right? And the frequency of f equals to 32 over 30 times 330. And the 330 divided by 30. So we're going to get 11 here. So we just need to count 11 times 32. So 32 times 11, 32, 32. So the answer is 352 hertz. So that's the frequency of tone F. Okay, the answer is bravo, right? Then the next one, for question number 22, we're still talking about tone, right? So it says that tone X has the frequency of 264 hertz. So this is the frequency of X is 264 hertz. And then you need to find out what is the frequency of the tone that is actually 1 octave higher than tone X. So we're going to say that we need to find the apostrophe Fx, right? So this is 1 octave higher. It's quite important for us to know, is it higher or lower, right? And now for the octave itself, octave is actually the ratio of C. Octave ratio is actually the ratio of the apostrophe C to C or high C to C. So it means that 48 to 24, right? And it say that the frequency that you need to find is the one that higher, right? So it's equal to 2 to 1 as well. So F apostrophe Fx to the, wait a second. Oh, sorry. Okay. Apostrophe Fx to the Fx supposed to be 2 to 1. So I'll count it somewhere else. I need a space here. So I'll continue here. So apostrophe Fx over Fx equals to 2 to 1. And then apostrophe X Fx is over 264 equals to 2. So apostrophe of X Fx is 2 times 264. So this is 528 hertz. So the answer is C, 528 hertz. That's question number 22. Okay. Next question number 23. Okay, you are given some information there. That's actually the factors, right? And then you need to find all the factors that determine the frequency produced by string. So it's actually related with the Mersenne law that said 1 F equals to 1 over 2L square root F over rho times A. Okay, so L is actually the length of the string or rope. F is actually the tension or the force given to the string. And then rho is the density. And then A is actually the cross-sectional area of the string. So the cross-sectional area, of course, it's also related with the diameter. And sometimes people also will say this about the thickness. So it's actually the same thing. The thickness, the cross-sectional area, or the diameter. Right, so diameter, yes. The length, yes. The amplitude, what does it mean with the amplitude? Okay, it's not having a relation with this formula. And the tension, yes. The density also, yes. So everything except 2. So we choose D because D doesn't have 2. So that's question number 23. The next one. Question number 24. Okay, question number 24, you are given some of the speed of sound. All right, it said that in air, wait, okay. In air, when the temperature is 0, okay, I think this one means air, it's mean air. Okay, air mean udara, right? Okay, and then here's also the air when the temperature is 15, okay. Okay, I have no idea what this air, all right, so let us check later. And then, oh, the air when the temperature is 0, so it's the speed is 331, and then when the air the temperature is 15, so the speed is 340. And then the fresh water at this temperature is has the speed, seawater has the speed, and the aluminum has the speed, and copper has the speed, right? So we just need to check the statement here, is it correct or not, right? So first statement, the speed of sound in air is smaller than in liquids because air molecule is denser than the liquid. If you say that smaller than liquid is correct, right? But the thing is, the denser one, it's not, the air molecule is not denser than liquid. So it's wrong because of this statement. And then the higher temperature of the medium, the smaller the speed. So if you see the air change the temperature and the speed is increased, so that's when we're talking about the fresh water. Okay, fresh water doesn't have it, but if we compare with the air, when the temperature is higher, the speed is getting faster. So it's mean not smaller one, right? So it's the higher the temperature, the speed is supposed to be faster. Okay, then the speed of sound in solid is greater than in fresh water. Okay, speed sound in solid. Okay, solid is the copper or all the aluminum. All right, so they are bigger. Yes, it's greater than the fresh water. That's correct. But then, because fresh water molecules are denser than solid, of course, no, the liquid is actually less denser if we compare it with the solid. So solid is actually denser. Okay, then for D, the speed of sound in liquid is greater than air. Yes, it's correct. Because the molecules of liquid are denser than air. Yes, finally. So the answer is D. So the molecule of the liquid is denser than the air. So that's question number 24. Okay, next question number 25. Oh, we still have a lot, yeah, until 30, I think. Okay, the speed of sound in air is 332 meters per second when the temperature is 0 degrees Celsius. So we can revert this as the VO. So V when the temperature is 0 degrees Celsius, this is 332 meters per second. And then the speed of sound in the air when the temperature is 25 degrees Celsius is, so this is the question. The question is asking what is VT? It's mean when the temperature now is 25 degrees Celsius. So we can count that VT is equals to VO plus 0.6 times delta T. The delta T here is actually revert to the difference, the time the 25 degrees Celsius with the 0 point here. So the VT is the question, all right? VO is 332 plus 0.6 times 25. So 332 plus 0.5 times 25 is 2.5 times 3. So it's 15, right? So VT equals to 347. Oh, yes, 347 meter per second. The answer is C. That's question number 25. The next one, question number 26. Okay, there is a ship here. Okay, the ship transmitted ultrasound wave to the seabed, right? And then the first reflection come 1 second after the transmission. So it's meant from the ship to the seabed and then back to the ship. The time taken is 1 second, right? And then while the second reflection comes 0.5 after the transmission. So be careful with what is the time given here. What is the reference of the time when actually it's counted? Is it after the transmission or is it after the reflection from the previous one? So here it's after the transmission. So for the second one, 1.5. So it's mean the time that travel by the sound from the ship to the seabed and then back to the ship. So the time is 1.5 second here. And as you know that this is actually, if we call this distance from the ship to the seabed is D1. So the times that is given as a D, that's given as a D 1 second is actually to travel for 2D, right? For 2 times of D1. And so that's the time here is actually for travel for 2D2, if this is the D2, right? And I will call this as T2 and I will call it as T1. And now what is the question? If the speed of the sound in the seawater was 1,400 meter per second, so the V is 1,400 meter per second, you need to count what is the difference in depth of the first and the second seabed. So actually asking what is the difference in D among them, right? So delta D of D2 minus D1. So of course we need to count what is D1 and D2 first, right? To count D1, we know that V is always distance over time, right? And here, the speed of the sound is given 1,400 meters per second. And then the distance that travel is actually for the D1. This is actually the 2D1, right? And then the times taken for this is actually T1. So 1,400 equals to 2D1 over T1 is 1. So 2D1 is equals to 1,400. So D1 is 700 meters. Okay, then the next one, in case of D2, in the case of D2, we know that the V is 1,400, the distance traveled is 2D2, and then the time is 1.5 seconds. So 1,400 times 1.5 seconds is actually 2 times of D2, right? So it's 2,100 meters is equals to 2D2. So D2 equals to 2,100 divided by 2, or 1,050 meters. So that's D2. So to get the difference in depth of the first and the second seabed, so we counted delta D equals to D2 minus D1. And here is 1,050 minus 700 is equals to 350 meter, right? So the answer is A. You also can use the quick way to solve it. So the difference in time for both of them is delta t is actually just 0.5 seconds, right? And then it used to travel back to back. So the time for one delta d is actually only 0.25. We divided it with 0.25 seconds. So to get the delta d, we just count this 0.25 times 1,400. So this is time times velocity speed. So you're gonna get the 350 meter as well. If you're okay with this quick way, it's okay, just do it. But I prefer you to do this complete way because I think it's better because you will know the concept, and also it's yeah, it has a small risk if we compare with counting this quick, right? Okay. Next, question number 27. Okay, it's about the resonance. Okay, the first resonance happened when the first resonance happened when the tuning fork can produce sound with a frequency of 350 Hz tapped against the end of the organ pipe as shown below, right? Okay, so the information that we got from the first line here is, okay, the order of the resonance is 1 because it's the first resonance. The frequency of the tuning fork is 350 Hz, right? It's given here, right? And then if the speed of sound on the air at the time is 350 meters per second. So we know that V equals to 350 meters per second. And then we need to find out what is the height of the air column. So question, we need to find what is h. And if you remember to answer this, h is always counted as 2n minus 1 over 4 times the lambda, right? Lambda is the wavelength. And the n here is given, but we don't have the information about lambda. So we need to count the lambda first. How you can get the lambda? We know the speed and also the frequency, right? So we can count the lambda first. So we use the V equals to lambda times F, right? So the speed is 350, and then lambda is question, and then the F is 350. Oh, it's easy, right? And then lambda is just 1. And what is this one? This is 1 meter, okay? And now we count for, we already get the lambda, so we can back to this equation. H equals to 2n minus 1 over 4. The n here is 1, so 2 times 1 minus 1 over 4 times the lambda is 1 meter. 1 meter, right? So it's 1 over 4 times 1 meter. Okay, the answer is in centimeters, so we change the 1 meter to centimeter, okay? So we're gonna get 25 centimeters. What is the height of the air column here? So the height of this air column here is 25 centimeters. Okay, so you can use this formula to get the to count about the resonance, or you can also remember that actually the order of the resonance is start from 1 over 4, 3 over 4, 5 over 4, 7 over 4, and so on. So it's actually the odd number. So this is the first order, second order, third order, and then fourth order. It's especially for the organ pipe, all right, the open-end organ pipe. For the different cases, we're gonna have a different formula, but that's not included with for our topic right now. Okay, that's question number 27. The next one, question number 28. The four pendulum are tied together to a crossbar shown below. When the pendulum X swing, so this one, X, all right? So the pendulum that will resonate with the pendulum X, and the correct reason is, so the answer, the one that will vibrate as well, that will resonate, is actually the one that has the same frequency. And among A, B, C, that has the same frequency is B. Why? Because the length of the rope is same with X. So it's supposed to be pendulum B because it has the same length of the rope. Okay, so let's answer question number 28. Okay, the next one. Okay, the next one is question number 29. It's about the Doppler effect, right? The ambulance is moving at a speed of 35 meters away from Tino, where Vino was stationary on the side of the route. So Tino is the observer, and the velocity or the speed of the observer or Tino here is 0 because it stopped, right? And then for the ambulance moving at a speed 35 centimeter away. So this is the VS, the field of the source of the sound, 35 meter per second away, right? And the question, if the frequency of the sirens given is 750 hertz, and this is the FS, right? You need to find what is the frequency of the siren heard by Tino. If the sound of the air, the speed of the air is 340 meter per second. Sorry, I should put it somewhere else. So V of the sound is 340 meter per second. And the question, you need to find out what is the F or the frequency that will be heard by the observer. So to count it, the frequency that will be heard by observer will be counted as V plus minus VO over V plus minus VS times FS. Okay, you can use your logic for this, or you can just memorize this thing. So when the observer is moving away, so the VO gonna be negative, all right? And then when the observer is coming toward the source, so the VO will be positive. So the idea is when the observer is coming to the source sound, so actually it's going to be louder. I mean, like the frequency going to be higher. So it's supposed to be positive. But when the VS is away, the VS will be positive because it's away. So it means that you need to hear the sound is having a lower frequency in our logic. So the VS will be positive. And then if it's closer or come closer, so the VS going to be negative. In our logic, it's going to be negative, so it's going to be smaller. So the frequency that heard by the observer are going to be higher. It's okay, you can use your logic or just memorize all of these things, right? And now, about this case, we're going to use the same formula that FO equals to V plus minus VO. But here VO is 0, right? So we just need to put 0 here, or same with just V or V only. And then as you know that here, the ambulance is actually moving away, right? When the ambulance is moving away, so the VS can be positive. So positive VS times FS. And now we just need to put the number. The V is the speed of sound on the air, right? So this is 340 over 340 plus VS is 35. Okay, and then times the FS is 750. So FO equals to 340 over 375 times 750. Okay, so it's actually, we can just cross it, divide by 375, divided by 375, we got 2, and we got 1 here. So 340 times 2 is 680 hertz. So this is the frequency that will be heard by the observer. And the answer is C. Okay, that's question number 29 about the Doppler effect. Okay, the last question, number 30. you are given some statement and then you need to find out which one is correct according the frequency of sound that can be heard, and it will be higher than its original. So the F the O will be bigger than Fs, right? So first, if the sound source is moving away from a stationary listener, no. If it's the sound source is moving away, so the frequency is going to be lower. The listener move toward the stationary sound source, yes, can be, right? The sound source and listener move away from each other, of course, it's going to be lower. The sound source and listener move toward each other, yes, of course, it's going to be higher. The sound source and listener move in the same direction at the same speed. So it's apparently nothing going to happen at this. They will just hear as what is the frequency of the sound source. So the answer here is 2 and 4. It's C. Okay, yeah, that's all the discussion about this question, about your mid-test question. So I hope it's gonna help you for preparing your mid-test. Good luck, everyone. God bless you, and make sure that you get a good score. Goodbye.